Okay, I'm on page 99, chapter 3. So let's get started, physics students. This topic is projectiles launched at an angle, and the information that will be given will be the angle at which it's launched from the horizontal, and the magnitude of the vector should be given as well. What you'll have to do is you'll have to resolve the y component, which would be vy initial. You'll have to derive that y component, and you'll also have to find the vx initial. The reason those two are important is because you need the vy initial in order to determine, well, let me just write it. It tells us how far the projectile is, not how far, how long, excuse me, how long, I was getting ahead of myself, how long the projectile is in the air, how long is Vx. So we'll do this with velocity in the y direction equals acceleration in the y direction times change in time, and that should look familiar. We've worked with that. The velocity x initial tells us how far the projectile will travel. It's sometimes referred to the horizontal, sometimes referred to as range. So, and I've also seen it. We before just have referred to it as x. That's what we've referred to it as. So, the other thing that's important to recognize is that this vector, this velocity y in the I direction, is going to be the same except for the negative at velocity y final and velocity y initial. These two vectors would be the same except for it would be the negative. So this vector would be positive on the way up, and then it'll be negative on the way down. You should also remember that we're always having a negative acceleration of 9.81. And the other thing that's important is that this horizontal vector that I just mentioned, this vxi, will remain constant throughout. That's the whole reason why this works, is that vector is constant. All right. So if you look at the formulas, on page, I wrote them here on my tablet. If you look at the formulas on page 99, there's 5 of them. The first formula, Vx equals Vxi, and as I said, it's going to remain constant. We'll solve for this one. That you'll definitely need. You'll need to be able to tell me the range, so that's important. So know that equation, and Vy final. I already said Vy final and Vy initial should be the same, but I'll show you how to determine that one as well. And then finally, there's 2 equations that are used if the launch and the landing are different. These last 2 are used if the launch and landing are different. Now, there's practice problems in your book. However, just as a warning, I'm not going to test you over an example where the launch and the landing is different. Just for the record, you won't see that on the exam. But you will see on the exam a problem exactly like number 34 on page 110. It's a review question, and if you're another one that you could work out after I've worked this one out, I think it would be helpful if you do if you do practice problem E on page 101, number 3. All right, practice problems E on page 101. Just do number 3 only. All right, don't do 1 through 3. Just do number 3. Okay, and I think that one is should be fairly representative of, and fairly simple. All right, so here we have a scenario where we've got an angle of 55 degrees, and we have a velocity. The initial velocity is 1.70 times 10 to the third meters per second. So here's that velocity vector. So what I'm going to need to do is resolve this vector first. So that's our step 1. Resolve the vector, because we need that x and the y components, as I said a second ago. And by the way, all we're going to do here is find the horizontal range. And also we're going to find time. All right, these are the only 2 things we're going to do here. Given the velocity of the vector and given the angle. All right, this is angle, and I'm doing problem number 3 on page 110. All right, so quickly we can resolve this. We did this before. 1.70 times 10 to the third meters per second times sine of the angle 55. So we're resolving y. That's why we're using sine. And this, as you know, we get from our SOHCAHTOA that you remember. Okay. Now this is, you put in your calculator, is 1.39 times 10 to the third meters per second. And then we resolve x, which is the exact same thing, except we're using cosine instead of sine, and that's 9.75 times 10 to the 2 meters per second. Right? So that's our first step. We need these numbers for sure, because, as I said earlier. And then the second thing we need to do is we need to find time. So if we find time by change in velocity in the y direction equals acceleration, which is 9.81 times the time. And just a reminder that the change in v equals velocity final minus velocity initial. So change in v equals a negative 1.39 times 10 to the third minus 1.39 times 10 to the third. And I apologize, I don't have units there, but I should put units there. Is negative 2.78 times 10 to the third meters per second. All right, that's how you find the change in velocity. So now that we have the change in velocity, we could just rearrange this equation so that we could solve for t, and that's negative 2.78 times 10 to the third meters per second over negative 9.81, which is due to gravity, meters per second squared. And that'll give us a change in time equals 200, I'm sorry, not 2.8. We could just, these are seconds, so there's going to be a bunch of them. 283.4 seconds. And let's see, 3 sig figs. We should stop at 3 sig figs, but 283 seconds. And now that we have time, we could go to our third step. Our third step is to find x. All right. So now we have time, we have the x and the y, and our third step is to find x. All right. X should be simple enough. Change in x equals velocity times change in time. So 9.75 times 10 to the second meters per second is our change in x that we've already worked out. If you hadn't worked this out, you could use the equation that I showed you earlier that has it for you, but I have already worked it out, times the seconds, which is 283, and that should give you x, or horizontal displacement, equals 1.58 times 10 to the 5th meters, 3 sig figs. All right.